Okay, so system A has 2 bricks, system B has 1 brick, moving at a constant speed to the right. So compare the net force. So the net force of both system A and B equals to 0 because there is no acceleration. And that's illustrated in this diagram, this free body diagram right here, where we have 5 forces in system A. One normal force goes up from A to the table. The force of the weight, the force of the hand exerted on A, and the force of friction of the table, and the normal force of A and B. In system B, we have 4 forces. The normal force going up and from the table, normal force of the weight, the weight force, and the normal force of B to A going to the right, and the kinetic friction force of B to the table. Is the magnitude of the forces on A to B greater, less than, or equal to the magnitude of forces exerted on B by system A? They are equal because both system is not accelerating, so they have 0 acceleration, so the magnitudes will offset each other. And would your answer change if it push it from the no, because the system accelerates will still equal to 0. So as the acceleration of the system equals to 0, the net force equals to 0. So all of the forces will have to equal to each other to offset each other, so it will equal to 0. Okay, so identifying the third laws by placing x's. So normal force of B to A is a third pair law of normal force from A to B, right here, these two. And what criteria to identify these force pairs? If you were to remove one of the pairs, the other would disappear. If you remove this one, this force would disappear. If you remove this force would disappear. And is your answer to C consistent with the identification of Newton's third? Yes, because the magnitude of normal force B to A equals to normal force of A to B. And when B is pushing on A is pushing back on B. It tells you to rank the magnitudes of the horizontal forces. So the greatest one is the force of the hand exerted on A, and then the kinetic force of A to the table, and then the normal force of A and B will equal to the normal force of B and A, which equals to the kinetic friction force of B to the table. As you can see in the previous diagram, these two has to add up to equal to this one. Well, okay, did you apply Newton's second law to compare the magnitudes of horizontal forces? So since there's no acceleration, the net force will equal to 0. So the addition of magnitude, the kinetic friction of A to the table, and the normal force of AB has to offset, so it will equal in magnitude but opposite direction of force of H hand exerted on A, which means this is the greatest force exerted, because these two add up to each other would have to cancel out this big force right here, so which makes this the greatest force. Okay, so and also in the system B there are only 2 forces in the horizontal direction, which means they are equal in magnitude but have to be opposite in direction for the acceleration to equal to 0. So these two forces are equal to each other because there's only two forces in the horizontal direction, and since the system is moving at a constant speed, which means no acceleration, these two have to equal to a net force of 0. So they are equal in magnitudes. How did I use the third law to compare the magnitudes of horizontal forces? So third law, I know these two were definitely equal. So normal force of AB and normal force of BA equal because as A pushes on B, B pushes back on A. Their magnitudes are equal. So what information besides the laws? The kinetic friction of A to the table is greater than the magnitude of the kinetic friction of B to T because it has a higher weight, which result in a higher normal force since the system has no acceleration. Since the system has no acceleration in the y direction, this W, wrong, sorry, this W is greater than this W, and this normal force has to offset this this weight, so this normal force is greater than this normal force, which result in a greater friction, kinetic friction over here than there is right here because of the normal force. The coefficient mu times the normal force will equal to the friction force, but since the normal force of this one is greater than this one, this friction force will be greater. Okay. And then, so I did some arithmetics, and I got the friction, kinetic friction of A to the table is 10 newtons, and the normal force of A to B is 5 newtons, and the force of the hand is 15 newtons, and normal force is 50 newtons, and the weight is 50 newtons of the first of system A. And then system B, the kinetic friction of B to the table is 5 newtons. The weight is 25 newtons. The normal force is 25 newtons. And the normal force from B to A is 5 newtons, which is the same because of 5 to 5, because of third law. So if you were to change the speed, would it change the answer? No, because the velocity does not matter when when it is at constant velocity. So if it's going at constant velocity, there is no acceleration. So the net force will equal to 0. So even if you half the speed or increase the speed by double, the acceleration will equal to 0, and all the forces will equal the same, be the same. If you're applying 15 newtons each time. So suppose push a brick. So if you change the friction coefficient, instead of it being at constant speed, like in the section 1, the system will actually speed up to the right. So it will accelerate to the right. According to the free body diagram, you can see that there's 5 forces here, and these two add up will be less than this long one. So the system's going to right. System A is going to right. Same goes with system B. The 4 forces add up with the net force of it going to the right also. As you can see, this one is less than this one, but these two are equal. So I agree with student 2 And she says, I think that they are speeding up since friction is less. So system A is pushing on system B, at a greater force than system B is pushing on system A. Well, you can see that because because the system is speeding up, as you can see, the free body diagram, and using the same forces, it will accelerate because there is less friction. There's more force going to the right than there is going back to the left. That's why the whole system is accelerating to the right. So rank the magnitudes or horizontal magnitudes of the diagram. So the top dog is, well, the force of the hand. And then it becomes the normal force of AB equals to the normal force of B to A, because they're third law pairs, which is greater or equal to the kinetic force of A to T. And the last force, which is the smallest force, is the kinetic force of B to the table. And it says, is it possible to completely rank the horizontal? It is not, because we are undecided on this part right here, because we don't have the acceleration. And we don't know if the friction is greater than a normal force or the normal force is greater than friction. We just know that it can equal or be greater to the normal force. Okay, last part says that if we treat the two system as a whole complete system, system C, they are the same and will be accelerating to the right also. So draw the free body diagram. Four forces: normal force going up, weight going down, force of the hand, and then friction. So the corresponding forces. So for the friction, we got the corresponding frictions, kinetic friction of A to the table and B to the table. And then for the weight, we also got the two weight of A to the earth and then B to the earth. And the same goes with the normal force of B to the table normal force and then A to the table of normal force. And then we just have the force of the hand of the hand exerting force on A, which is the corresponding force. So the forces that are not listed are the normal force between A and B, because they're third law pairs. That's the only characteristics that are not in that have in common that none of these have, is that they're third law pairs, and they're the only force that does not exist in this diagram. Why is it not considered these forces determine the motion of? As you treat the two system as one whole complete system, the inner forces, which is the force between those two systems, will disappear, and you will only see the whole picture. So the forces are defined as the internal forces, which mean that as a system they basically don't exist, or they don't matter. So when you draw this diagram of this cart, it's accelerating to the right and it's not accelerating up and down because the magnitude cancels out, and then net force is to the right, so the cart is moving towards the right. So with this tension pulling this way in the angle of 45, it looks like. So that's it. Alright.